So we were discussing internal energy calculations and constant volume calorimetry, or BOM calorimetry, which is used to calculate internal energy by measuring the heat of a reaction. Okay, so with that established, let's now discuss a somewhat annoying aspect of calorimetry, which is this idea of calorimeters and calorimeter constants. Well, calorimeters themselves often absorb a small amount of heat exchanged in the chemical reaction and heat transfer processes. This heat transferred to the calorimeter must be accounted for in our heat transfer equation. Now, in order to get a sense of how much heat your calorimeter is absorbing or releasing, we measure this by mixing samples of water at different temperatures and measuring the final temperature of our mixture. The final temperature should be the same for all samples. So the water and all the water in your calorimeter will eventually reach thermal equilibrium, and they'll eventually be at the same temperature. In this case, heat lost by the warm water is gained by the cold water and the calorimeter. So notice how the calorimeter is also participating in heat exchange. So to draw a picture to help us get a sense of what's going on in this process. And so let's pretend we have our calorimeter. Okay, and to that calorimeter, we mix some hot water, and we mix the hot water with some cold water, okay? So thinking about our heat transfer process, so at our high temperature water mixed with our low temperature water, heat will flow from our hot water to the cold water. In addition, heat will also flow to our calorimeter. So as heat is exchanged with low temperature water and the calorimeter. So then, there are two things receiving heat from our heat transfer process. And as such, any heat lost by our hot water is gained by the cold water and our calorimeter. Does everyone see this key distinction? Does everyone see what's different about this equation? Does everyone see that there are two terms in our heat exchange expression now? Because we have two things that are absorbing heat or releasing heat. Does that make sense so far? Now, we know that for solutions, we can measure the heat associated with the heat transfer of the hot and the cold water by taking the mass times the specific heat times the T final minus the T initial. Now, for the calorimeter, we already have an expression to measure the heat gained by the calorimeter, and that's our calorimeter heat capacity times the T final minus the T initial of our calorimeter. Now, one thing I'd like you to note is that the T initial of our calorimeter is the same as that of our cold water. So substituting, we have the Q of the hot water is equal to the -1 times the Q of the cold water plus the Q of your calorimeter. Now, I can show the algebra, but if you solve this algebraically, we get the following expression for the calorimeter constant for your calorimeter. So this allows us to determine how much heat is absorbed by our calorimeter when we run a reaction inside a calorimeter. You will almost always in the real world have to calculate a calorimeter constant, or you'll be given a calorimeter constant in a problem. Does everyone understand what this calorimeter constant represents? It represents the fact that the calorimeter is participating in heat exchange, and we need to account for heat absorbed by our calorimeter. So we need to figure out, well, how efficiently does the calorimeter absorb or release heat? Does that make sense? Can I get some confirmation in the chat that everyone's comfortable with this idea? Now, I'm not expecting you to memorize the equations, but I will expect you to be able to derive this equation. So to go through this step-by-step derivation, just like we did. It is a long equation, but I like to think about each of my equations in terms of what is each set of numbers representing. And if you think about it like that, it's easier to memorize, or it's easier to remember the individual pieces. Okay, so let's put this equation into practice. Things are memorized via application. So the specific heat of our calorimeter is given by the following equation. So let's say we're trying to figure out the heat capacity of the calorimeter. If 100 grams of water at 100 degrees Celsius are added to 100 grams of water at 25 degrees Celsius, and the final temperature is 61 degrees Celsius. Okay, so the mass of our hot water is going to be 100 grams. The temperature of our hot water is going to be 100 degrees Celsius. The final temperature is 61 degrees Celsius. The specific heat of water is 4.184 joule per gram degree Celsius. The mass of cold water is 100 grams. The temperature initial of our cold water is 25 degrees Celsius. The temperature final is 61 degrees Celsius, and the specific heat of water is 4.184 joule per gram degree Celsius. Now all we have to do is plug in our numbers. So the specific heat of, the heat capacity of our calorimeter is the mass of our cold water, which is 100 grams, times the specific heat of water, which is 4.184 joule per gram degree Celsius, times T final, which is 61 degrees Celsius, minus the T initial of our cold water, which is 25 degrees Celsius, minus the mass of our hot water, which is 100 grams, times the specific heat of water, times T final minus T initial, which is 61 minus 100 degrees Celsius for our hot water, divided by, let's keep going in this equation, T final minus T initial cold. So we have 61 degrees Celsius minus 25 degrees Celsius. So if we punch this into our calculator, this in turn will give us the specific heat of, the heat capacity of our calorimeter. So let's enter that into our calculator. So we have 100 times 4.184 times 61 minus 25 minus 100 times 4.184 times 61 minus 100. And then we're going to take our answer and divide it by 61 minus 25, which in turn, let me just check that everything, oops, one moment, sorry about that. Okay, so punching this into our calculator, punching this expression into our calculator, I'm just checking my work right now. For these problems, you have to be pretty meticulous to make sure that there's no error. So at the end of this calculation, we get a heat capacity of 872 joule per gram. Let's just check. Let's just check our, no, sorry, joule per degree Celsius, because grams cancel, degrees Celsius cancels. And we're left with joule per degree Celsius, which is the correct units for heat capacity. So the units are correct. So the units really are your guide here. So make sure to check your units. So when you entered your data into your own calculator, did you get a similar result for the heat capacity of your calorimeter? Did you get a similar result for the heat capacity of your calorimeter? Is this making sense so far, how to calculate the heat capacity of your calorimeter? Okay, so now that we have this established, I'd like you to attempt the following problem and try to calculate the heat capacity of the calorimeter for the following experiment. And we'll discuss this example in about 4 minutes. So try to use the above equation to calculate the heat capacity of your calorimeter given the following information. And we'll discuss this example in about 4 minutes. Yeah, the density of water can be approximated to 1 gram per mil. Yep. So you can convert the volume of water into the mass of water. And we'll discuss this example in about 2 to 3 minutes. Let's try to get a few responses in the chat for the heat capacity of our calorimeter for the following water mixing experiment. Yep, 60 degrees is correct for the hot water, 25 degrees Celsius is correct for the cold water. Just keep in mind that I said that the temperature rises 15 degrees Celsius, not that the final temperature is 15 degrees Celsius. So try to dissect what that phrase means, as this is really important to determining your final temperature. But the responses and setup I see in the chat looks good, look good so far. Yep, and the response I see in the chat looks perfect. Let's spend about another minute and a half on this question, and then we'll discuss this example. Okay, so let's discuss this example. So the mass of our hot water is 40.0 milliliters, which we know we have 1 gram per milliliter of water, which gives us 40.0 grams. The initial temperature of our hot water is 60 degrees Celsius. The final temperature is 25 degrees Celsius plus 15 degrees Celsius because our temperature rises. That gives us 40 degrees Celsius as our final temperature. The specific heat of water is 4.184 joule per gram degrees Celsius. The mass of the cold water is 40 milliliters times 1 gram per mil, which gives us 40 grams. The initial temperature of our cold water is 25.0 degrees Celsius. The final temperature of our cold water is going to be 40 degrees Celsius. And then the specific heat of water is equal to 4.184 joule per gram degrees Celsius. Okay, so solving this, the heat capacity of our calorimeter is equal to the mass of our cold water, which is 40 grams, times the specific heat, which is 4.184 joule per gram degrees Celsius, times T final minus T initial, minus the mass of hot water, times the specific heat of water, times T final minus T initial. Okay, now divided by, let's just check, the temperature final minus the temperature of our cold water. So we have 40 minus 25 degrees Celsius. Let's just check that we did that in the earlier problem. Yep, okay, perfect. Okay, so now all we have to do is punch this into our calculator. So that gives us a heat capacity of our calorimeter of, so we have 40 times 4.184 times 15 minus 40 times 4.184 times negative 20. Then we take our answer and we divide it by 15. And that in turn gives us a heat capacity of our calorimeter of 391 that we round to 390 joule per degree Celsius. So your heat capacity should always be a positive number, and it should have units of joule per degree Celsius. The temperature rises relative to your cold water temperature. Sorry, this would be, we're rounding down because our input, let me show you here, 3 sig figs, this should be 40.0. Oh, we don't have to round. All of our inputs have 3 sig figs, so we can keep this as 391 joule per degree Celsius. Any other questions on this example? Any other questions on this example? Okay, so let's discuss another case now that we've discussed how do we actually measure calorimeter constants. In case number 2, we have a bomb calorimeter containing a variable volume of reaction solution, and the calorimeter participates in heat transfer. So when the reaction releases heat, the heat is absorbed by both the calorimeter solution and the calorimeter itself. So again, if we have our reaction, it is going to be releasing heat and exchanging heat with both our solution and the calorimeter itself. So then we need to reflect that in our heat transfer expression. So we'll often be given the heat capacity, the calorimeter, or we can measure the heat capacity of our calorimeter. Now, a key signpost that you're dealing with this type of problem form is that you're given the mass of water or a solution in the problem guidelines. Okay. So in this case, the change in internal energy for our system, which is our reaction, is equal to the heat of reaction, which is equal to the heat absorbed by our surroundings. In this case, we have both our calorimeter and water absorbing heat as part of our surroundings. So then we know previously that Q calorimeter is just the heat capacity of our calorimeter times the change in temperature, and the heat absorbed by our water or the solution is just the mass of water times the specific heat of water times the change in temperature of water. Okay, so we'll be given the heat capacity of the calorimeter or the mass of water present in our calorimeter. Yes, for QCal, you don't have a mass because it's the heat capacity of the calorimeter. which is specific to whatever calorimeter you're using. Remember, the distinction between heat capacity and specific heat is that heat capacity is specific for a sample of a given mass, while specific heat is true for all samples of that chemical identity. And so to calculate the heat, if you're given the specific heat, you need the mass. Perfect. I'm glad that answered your question. So let's show how this problem-solving manifold works in practice. So if we take 500 milligrams of naphthalene and we combust it in a bomb calorimeter containing 1,000 grams of water, and we notice the temperature of our water increases from 20 to 24.37 degrees Celsius, and our calorimeter constant is 420 joule per degree Celsius, we're asked to figure out what is the change in internal energy for the reaction. So we know that the mass of our sample is 500.0 milligrams of naphthalene. This is a distractor number. It doesn't actually go into our internal energy equation. We'll use this a little bit later on. The mass of water, that's our key signpost, is 1,000 grams, okay? The temperature initial of our water, which is equal to the initial temperature of our calorimeter, is 20.00 degrees Celsius. The temperature final of water, which is equal to the temperature final of our calorimeter, is 24.37 degrees Celsius. Okay. We also know that the calorimeter constant is equal to 420 joule per degree Celsius. We also know the specific heat of water is equal to 4.184 joule per gram degree Celsius. So now that we've written out what we know that the change in internal energy for our system is -1 times the heat capacity of our calorimeter, which is 420 joule per degree Celsius, times the change in temperature, which is 24.37 minus 20.00 degrees Celsius, plus the mass of water, which is 1,000 grams, times the specific heat of water, which is 4.184 joule per gram degree Celsius, times the change in temperature, which is 24.37 minus 20.00 degrees Celsius. So punching this into our calculator, that gives us a change in internal energy One moment, just punching that into my calculator. And that gives us a change in internal energy of negative 20,119 joules. We know there are 10 to the negative, in 1 kilojoule, there are 10 to the negative third joules. Whoops, sorry, 10 to the positive third joules. And that in turn gives us negative 20.1 kilojoules for our change in internal energy. Does this example make sense to everyone so far? Does this example make sense to everyone so far? It's just kilojoules, yep. the degrees Celsius have canceled out. Energy has units of joules or kilojoules. Any other questions on this example? The mass of the sample doesn't matter in terms of the calculation. It can be used to calculate the enthalpy per mole for this reaction, but the mass of the sample, since the sample is not part of the solution, it's not included in that heat transfer expression. Does that make sense? Perfect. So let's try to apply what we've learned so far to the following example, where we look at the combustion of trinitrotoluene, or TNT. So let's work on this problem for about 5 to 6 minutes, and then we'll come together as a group to discuss. And if you have any questions or if you want to submit your proposed response, don't be shy to type in the chat. So remember that for the second mass, you're using the mass of water, not the mass of your sample. The mass of your sample is irrelevant for the first part of this internal energy calculation. The mass of your sample is used to calculate the enthalpy per mole. But for the initial calculation for the heat of reaction, you need the mass of water rather than the mass of your sample. Other than that, the responses I see in the chat look great. And we'll discuss this example in about another 3 minutes. And the responses I see in the chat look very reasonable so far. And we'll discuss this exam. Sorry, is that joules or kilojoules? For the response I see in the chat, I would just double check that your magnitude is correct and that your units are correct for that response. It should be a relatively large amount of heat generated. And we'll discuss this example in about another 2 minutes. Okay, perfect. And that response in kilojoules looks perfectly reasonable. No problem at all. I'm always checking just because the units can affect or have a pretty dramatic effect on these problems. And we'll discuss this example in another minute. Okay, so let's discuss this example. So first and foremost, we know that the heat capacity of our calorimeter is 534 joule per degree Celsius. The initial temperature of our calorimeter is 23.4 degrees Celsius, which matches the initial temperature of our water. The final temperature of both our water and our calorimeter is 26.9 degrees Celsius. Okay, we also know that the mass of water is so we take 675 milliliters times 1 gram per milliliter to give us 675 grams of water. And then we also know that the specific heat of water is 4.184 joule per gram degree Celsius. Okay, now punching this into our expression, the change in internal energy is equal to the heat of reaction, which is equal to -1 times the heat capacity of our calorimeter times T final minus T initial plus the mass of water, which is 675 grams, times the specific heat of water, which is 4.184 joule per gram degree Celsius, times T final, which is 26.9 degrees Celsius, minus T initial, which is 23.4 degrees Celsius. And that in turn gives us a change in internal energy for this reaction. Let's now punch this into our calculator. So we have 534 plus 26.9 minus 23.4. Okay, plus 675 times 4.184 times 26.9 minus 23.4. And that in turn gives us an enthalpy of reaction of negative 11,753 joules. We know in 1 kilojoule, there are 10 to the third joules. That gives us negative 11 points, well, we'd round it up to 11.8 kilojoules for the change in internal energy of this specific reaction. Does this example make sense to everyone? Any questions on this example? Any questions on this example? Did you get the same response in your calculator? Okay, if we don't have any other questions, let's keep going and let's look at another case for calorimetry. So the third case that we commonly see in bomb calorimetry is where heat transfer to the calorimeter is negligible. If heat transfer to the calorimeter is negligible and can be ignored, the calorimeter term disappears from our equation, and the change in internal energy of our system is equal to the heat of our surroundings times -1, which, if our surroundings are a solution of water, this simplifies to -1 times the heat absorbed or released by our water solution, which in turn is just the mass times the specific heat times the change in temperature. So let's show how we can apply this equation for this calorimetry calculation. So for example, if we have a 252 milligram sample of benzoic acid that we burn in a bomb calorimeter, we know it has 814 grams of water at 20 degrees Celsius. So the mass of water is 814 grams. The initial temperature of water is 20.00 degrees Celsius. The reaction increases the temperature of the water to 21.70 degrees Celsius. So the T final of our water is 21.70 degrees Celsius. And it's asked, what is the internal energy released by this process? Now, one thing that I'd like you to pay special attention to, does this problem ever mention a calorimeter constant? Do we see a calorimeter constant or any data that we could use to calculate a calorimeter constant? Yeah, we don't have any information or any indication of a calorimeter constant, so this is clearly the case where heat transfer to the calorimeter is likely negligible. So we also know the specific heat of water is 4.184 joule per gram degree Celsius. So now we have all the information we need to calculate the change in internal energy for this reaction, which is -1 times the mass of water times the specific heat of water times T final minus T initial, which in turn gives us a change in internal energy for this reaction of 814 times 4.184 times 1.70, which gives us negative 5,790 joules. And we know in 1 kilojoule, there are 10 to the third joules. So that gives us negative 5.790 kilojoules of energy released for our change in internal energy. Does this question make sense so far? It's essentially an easier version of the earlier example that we did. Any questions on this example? Yes, the 5,790 was rounded from 5,789.8. We rounded to 3 sig figs. So if there's no calorimeter constant mentioned, you can assume that the heat transfer associated with the calorimeter is negligible. Yep. If there aren't any other questions, let's try to apply what we've learned to another example. So suppose we're combusting another sample of benzoic acid. I'd like you to calculate the change in internal energy associated with this process. And we'll discuss this example in about 4 to 5 minutes. And the response I'm seeing so far in the chat looks reasonable. Let's try to get a few more responses in the chat before we discuss. And if you have any questions or would want to submit your proposed response, don't be shy to share it in the chat or verbally using the voice chat feature. And we'll discuss this example in about another 2.5 minutes. Yes, so if the change in internal energy is negative, essentially what that's implying is the reaction is releasing heat and that heat is absorbed by the surroundings. And again, remember in your calculations that you want to use the mass of water, not the mass of your sample. And your response should be in the order of kilojoules. It should definitely be greater than 1 kilojoule. So just check your calculations and make sure that your inputs don't have any calculator errors. And we'll discuss this example in another minute. Okay, so let's discuss this example. So we know first and foremost that the mass of water is 724 grams. The initial temperature is 22.50 degrees Celsius. The final temperature is 23.39 degrees Celsius. And the specific heat of water is 4.184 joule per gram degree Celsius. Okay. Perfect. So we know that the, sorry about that. So we know that the change in internal energy is equal to negative Q surroundings, which is equal to -1 times the mass of water, which is 724 grams, times the specific heat of water, which is 4.184 joule per gram degrees Celsius, times T final, which is 23.39 degrees Celsius, minus T initial, which is 22.50 degrees Celsius. That in turn gives us a change in internal energy of negative 2,700. Sorry, more correctly, 2,696 joules, which we in turn convert, since we know that we have 10 to the, in 1 kilojoule, we have 10 to the third joules. That gives us negative 2.70 kilojoules, rounded to 3 sig figs to match the number of sig figs in our inputs. Does this example make sense? The responses I saw in the chat and the setups I saw in the chat were perfect so far. Okay, if I don't see any other questions, let's continue on and let's talk about enthalpy. So enthalpy is defined as the heat transferred at constant pressure. So enthalpy can be thought of as the sum of the internal energy and the product of the external pressure and volume. So you can think of this PV term as essentially to have an object be present in an environment. To put an object into that environment, you're displacing a certain volume and a certain pressure. So you can think of this delta PV term as the amount of energy required to have your object in a given volume at a given pressure. Okay. So at constant pressure, this delta PV term, the pressure is constant. So we can move the pressure out of this delta term because the pressure is not changing. Now in turn, that gives us delta H is equal to delta E plus P delta V. We know that delta E is equal to Q plus W, which is equal to Q plus, well, in this case, minus P delta V. So if delta H is equal to delta E plus P delta V, we in turn get delta H is equal to Q plus W plus P delta V, which is equal to Q minus P delta V plus P delta V. the P delta V term cancels, and under constant pressure, we get the enthalpy is equal to the heat transferred, or, well, yes, the heat transferred at constant pressure. Enthalpy, also critically enough, is what's known as a state function. It only depends on the final and initial state of our system. So we can do a lot of tricks associated with state functions. So the fact that enthalpy is a state function makes calculations involving enthalpy quite convenient. Any questions so far on this idea? Okay, so now continuing on, the way that we measure the heat exchange under constant pressure, the way that we measure enthalpy is via constant pressure or coffee cup calorimetry. We actually did coffee cup calorimetry last class session. So we know that most reactions that we run on a day-to-day basis are run under a constant pressure of the ambient atmospheric pressure. Thus, when we measure the heat exchanged by a reaction, under most conditions, we are measuring the heat of reaction at constant pressure. So here's a typical coffee cup calorimeter setup. We've actually used a coffee cup calorimeter before in the laboratory that we performed yesterday. Okay, so just like our constant volume calorimetry, there are a few different cases for calorimetry under constant pressure. So in case one, the calorimeter will participate in heat exchange. So just like before, when the reaction releases heat, the heat is absorbed by both the calorimeter solution and the calorimeter. Now, the heat capacity of the calorimeter will almost always be given, and it's unique for each calorimeter setup. Now, what's really important for coffee cup calorimetry is that when the reactions run in the calorimeter, the total mass of all solids and solutions added to the calorimeter will absorb heat released by the reaction. Further, the calorimeter solution will have a slightly different specific heat depending on the chemical reaction or solution identity. It's not going to be pure water anymore. The reaction is occurring in solution, and the solution is absorbing or releasing heat accordingly. Sorry, the solution is absorbing heat from the reaction. So you will almost always see a unique specific heat for the calorimeter solution. Though in general, most solutions in water will have a heat capacity close to that of pure water. Okay, so we can write out the enthalpy as the heat of reaction at constant pressure, which is equal to negative Q surroundings. And in this case, for our surroundings, we have our calorimeter and our water absorbing the heat. So just to draw a picture, just to help us see what's going on here. So suppose we have a reaction. So suppose we have a reaction, which I'm going to draw as a little box to just help us visualize what's going on. So as our reaction occurs, it will release heat into our solution, and it will release heat into our calorimeter. So we have to account for heat exchange with both components of this system. Now, unlike in bomb calorimetry, our reaction mass is dissolved in water. And as a result, we have to look at the total mass of the solution after mixing all of our reagents. Okay, so this turns into, we have Q cal, which is just C cal times delta T. And the heat associated with water, which we'll call Q solution, is just the mass of the solution, which is the total mass of the solution in the calorimeter, times the specific heat of the water solution, which will either be very close to water or it will be given in the problem. And delta T is the temperature change of the calorimeter solution. Now, to calculate the molar enthalpy, we take the heat of reaction and we divide by the moles of limiting reactant. More on that later. Okay, so now that we have this framework in place for visualizing coffee cup calorimetry and recognizing the fact that the calorimeter and reaction solution are both participating in heat exchange. Yes, the solution is not just going to be water. In coffee cup calorimetry, the reaction and the reservoir, or the calorimeter solution, are in contact with each other and they're mixed together. So then the total mass of our solution is not just the mass of water, it's the mass of water plus everything else that we mix together in our calorimeter. That's exactly right. Does that make sense? Did that answer your question? Okay. So let's look at a practical example now. So in most cases, and such as in the experiment that we performed yesterday, heat exchange with a calorimeter is often going to be negligible in nature. In this case, the calorimeter term cancels out and we're just left with Q reaction is equal to -1 times Q solution, which we write as MC delta T. Let's look at an example where we apply this equation and we calculate the enthalpy of reaction, the heat of reaction, and the molar enthalpy of reaction. So in this case, we have a mass of 0.103 grams of zinc. Okay, the mass of hydrochloric acid is going to be equal to the density times the volume. If we know the density, we just take 1.0 gram per mil times 50.0 milliliters, which gives us 50 grams. Now, just to draw a picture of what's going on, So initially, we're going to have our solution. So we have our solution of hydrochloric acid. And we are going to drop in some zinc. They will react, and in turn, heat will be released into our solution. So then, my question to all of you is, what is the total mass of solution? What's the total mass of the zinc and hydrochloric acid that we mix together? So we take our 50 grams of hydrochloric acid, and what do we add to that? Did we add anything else to our solution? Yep, we have to add the mass of zinc. So we have 50 grams plus 0.103 grams, which gives us 50.103 grams total for our solution. Wonderful. So we know the specific heat of our solution is 4.18 joule per gram degrees Celsius. We know our T final is 23.7 degrees Celsius. Our T initial is 22.5 degrees Celsius. So now we have all the information we need to calculate the heat of reaction. And the heat of reaction in this case is equal to -Q solution. So we have -1 times the mass of our solution times the specific heat of our solution, which is slightly different from that of water, times T final minus T initial. That in turn gives us a heat of reaction. And now let's punch that into our calculator. So we have 50.103 times 4.18 times 1.2. And that in turn gives us 251 joules, okay? Negative 251 joules because we have the negative sign. Now we're going to calculate the molar enthalpy of reaction, which is 251 joules. So Q over N. So to calculate the moles of zinc that reacted, we're going to take our 0.103 grams of zinc, and we know that in 1 mole of zinc, we have how many grams? What is the molar mass of zinc? What is the molar mass of zinc? 65.38. Okay, so punching that in, that gives us a moles of zinc equal to 0.001565 moles of zinc. Now let's calculate the enthalpy. So the enthalpy is equal to Q over N. We have negative 251 joules over 0.001565 moles of zinc, which gives us 160,383. So let me just check this one more time. 0.103 over 65.38. Okay, so we have 251 over 0.001565, which gives us negative 160,383 joules per mole of zinc. And we know that we have 1 kilojoule, we have 10 to the third joules. So that gives us oh, this should be 1575. Yep, that looks right. So let's punch this into our calculator. So we have 251 over 0.001575. That gives us 159,365 joules per mole. Converting to kilojoules, our enthalpy gives us negative 159 kilojoules per mole of zinc. So we were able to calculate the molar enthalpy of reaction of zinc with hydrochloric acid. Does this example make sense to everyone so far? Any questions on this example? Any questions on this example? Okay, so let's try to apply what we've learned. And now that we've gone through and we've showcased an example where we've calculated the enthalpy of reaction, let's consider another facet of these types of problems, which is the relationship between enthalpy and limiting reactants. So enthalpy is the heat absorbed or released by a reaction at constant pressure per mole of reactant that actually reacts. So the key word is the reactant has to react to absorb or release heat. If there is a limiting reactant, the excess reactant does not completely react, and thus it will not generate or absorb heat. Thus, to calculate enthalpy, we take the heat of reaction over the moles of reactant that are consumed during the chemical reaction. For example, we can write this as like kilojoules per mole of hydrogen. You need to be specific in your chemical equation what reactant you're referring to when you talk about enthalpy. Now, the excess reactant can still act as a calorimeter solution, and it still absorbs heat produced by the chemical reaction. As such, you want to make sure you use the total mass of the calorimeter solution. Okay, so let's look at an example. So suppose we take 50 milliliters of sulfuric acid and we mix it with 50 milliliters of sodium hydroxide at 25 degrees Celsius. The solution raises to a final temperature of 31.7 degrees Celsius, and we're asked to calculate the heat of reaction. We can assume the specific heat of the solution is 4.18 and the density is 1 gram per mil, and that the calorimeter absorbs a negligible amount of heat. Okay, so first let's look at the following equation. We have to get an equation for this. We have sulfuric acid reacting with sodium hydroxide in order to give water and sodium sulfate. So this is your typical acid-base reaction. Now my question to all of you, and this is really important, now that we have our chemical equation, is this equation balanced? Is this equation balanced? No, it's not. So as we see, we have 2 sodiums on the right, so we need 2 sodium hydroxides on the left. Additionally, we have 4 hydrogens on the left, so we need 2 water molecules for a total of 4 hydrogen atoms on the right. So now that we have the equation balanced, let's in turn identify our limiting reactant. And we're going to use a shortcut here. We're going to figure out the moles, and we're going to divide by our reaction coefficient. And the smaller number indicates the limiting reagent. Okay, so let's take a look at this idea. So in this case, the moles of sulfuric acid are equal to 50.0 milliliters times 10 to the negative third liter per mil times 0.987 moles of sulfuric acid per 1 liter. So punching that into the calculator right now, we have 50 over 1,000 times 0.987, and that in turn gives us 0.04935 moles of sulfuric acid. Now, we're next going to calculate the moles of sodium hydroxide. The moles of sodium hydroxide in this case are 50.0 milliliters times 10 to the negative third liter per mil times 1.00 moles of sodium hydroxide per 1 liter. That gives us 0.0500 moles of sodium hydroxide. Now we can't just compare the moles. We have to figure out our limiting reactant using the stoichiometry. So thinking about the moles of sodium sulfate from sulfuric acid, if all of our sulfuric acid reacts, we'd have 0.04935 moles of sulfuric acid times 1 mole of sodium sulfate per 1 mole of sulfuric acid, and that would give us 0.04935 moles of sodium sulfate. Okay, let's do the same calculation from our product method for the moles of sodium hydroxide, which gives us 0.0500 moles of sodium hydroxide, and we're going to calculate the moles of sodium sulfate generated from sodium hydroxide. So we have 1 mole of sodium sulfate per how many moles of sodium hydroxide? What is our stoichiometry in this equation? Is it 1-to-1 or 2-to-1? What is our stoichiometry for sodium hydroxide? What is our stoichiometry for sodium hydroxide? What is our stoichiometry for sodium hydroxide to sodium sulfate? What is our mole to mole ratio? 1-to-2. This is really important because these problems are still fundamentally built on the scaffolding of limiting reactants. So we see when all of our sodium hydroxide reacts, we only get 0.025 moles of sodium sulfate. So which reactant is limiting? What is limiting? Sodium hydroxide or sulfuric acid? Which reactant is limiting? Which reactant is consumed first and generates the least amount of product? Which reactant is limiting? Sodium hydroxide, exactly right. So sodium hydroxide is limiting, and we know that we have 0.050 moles of sodium hydroxide reacted. Okay, so now that we have that out of the way, we're ready to begin addressing the rest of this problem. Okay, so now that we know that sodium hydroxide is limiting and we have 0.050 moles of sodium hydroxide reacted, let's read off the rest of the data that we have from the problem. We know that the volume of sodium hydroxide is equal to 50.0 mils. We know the volume of sulfuric acid is 50.0 mils. So then we know that the mass of the sodium hydroxide solution is 50.0 mils times 1 gram per mil, which gives us 50.0 grams. Likewise, the mass of the sulfuric acid solution would also be 50.0 grams. Okay. We know that the specific heat of the solution is 4.18. Let me just check to be sure. 4.18 joule per gram degree Celsius. Okay. We know that the initial temperature in this case is 25 and the final temperature is 31.7. So now what we're going to do is we're going to calculate the heat of reaction, which is equal to the heat of solution. and that's equal to the mass of the solution in total. So what do we do with these 50 grams of our two solutions that we mix together? What do I do to each of these? I add them together. So I have 50.0 grams plus 50.0 grams. That's our mass of solution times the specific heat of the solution, which is 4.18 joule per gram degrees Celsius, times delta T, which is 31.7 minus 25.0 degrees Celsius. And that in turn gives us a heat of reaction of 100 times 4.18 times 6.7. And that gives us a heat of reaction of negative 2,800 joules. We know that we have 10 to the third, in 1 kilojoule, we have 10 to the third joules. That gives us negative 2.80 kilojoules. And now to complete this problem, to calculate the enthalpy of reaction, we take the heat of reaction over the moles, which gives us negative 2.80 kilojoules divided by 0.05 moles of sodium hydroxide, which in turn gives us negative 56.0 kilojoules per mole of sodium hydroxide. And just as an interesting piece of trivia, the molar enthalpy of neutralization for most strong acids, strong base neutralizations is about 56 kilojoules. Any questions for this example? Any question on this example? So it's a combination of the limiting reactant and our enthalpy calculations. So to test that we're comfortable with this idea, let's try to tackle the following problem. I want you to identify the limiting reactant, and I'd like you to calculate the enthalpy of reaction per mole of limiting reactant. So this is a long problem, so let's take about 3 to 4 minutes, and let's first identify the limiting reactant. Once we have the limiting reactant, then we'll spend another 4 to 5 minutes calculating the heat of reaction and molar enthalpy of reaction. So let's take about 4 minutes and calculate and identify the limiting reactant, and we'll discuss the first part of this question in about 4 minutes. And if we have any questions, or if you'd like to submit your proposed responses for the balanced equation and the proposed response for the limiting reactant, don't be shy to type it in the chat. The balanced chemical equation is really key in this reaction, and it requires us to remember our rules for balancing reactions, specifically balancing acid-base reactions. And the balanced equation I see in the chat looks good. Let's spend about another 2 to 3 minutes on the first part of this example, and let's just try to identify the limiting reactant. And if you have any questions, don't be shy to ask them in the chat or unmute and ask your question verbally. This is about the level of difficulty of a question that you'd see on the exam and in the quizzes this week. And the assignment of the limiting reactant that I see in the chat looks great so far. And we'll discuss the first part of this question in about another minute and a half. And we'll discuss this example in about another 30 seconds to a minute. Let's try to get a few more responses in the chat. Okay, so let's take a look at the following problem. So first and foremost, we have hydrochloric acid reacting with calcium hydroxide. And in terms of our acid-base reaction, our products are going to be water and then a salt. So we take calcium 2+, cross it with chloride. That gives us our product, calcium chloride. Now, I have to ask this question again because I want you always to be repeating this question when you look at a chemical reaction. Is this equation balanced as written? Is this equation balanced as written? No. We have 2 chlorines on the right, so we need 2 chlorines on the left. We have 4 hydrogens on the left, so we need 4 hydrogens on the right. So now that we have our balanced equation, now let's go through and let's calculate the moles of each of our reactants. So the moles of hydrochloric acid are equal to 50.00 mils times 10 to the negative third liter per mil times 0.125 moles of hydrochloric acid per 1 liter. So punching that into our calculator, we have 50 over 1,000 times 0.125. That gives us 0.00625 moles of hydrochloric acid. Okay. We can also calculate the moles of calcium hydroxide, which is 50.00 mils times 10 to the negative third liter per mil times 0.125 moles of calcium hydroxide per 1 liter, which gives us 0.00625 moles of calcium hydroxide. Now, just to check to make sure, do we have enough information right now to identify our limiting reactant? Do we have enough information right now? No, we don't. Limiting reactants aren't just based on the number of moles, they're based on the stoichiometry. That's exactly right. It's always important that we're being attentive of these facts. So now the moles of, let's do calcium chloride from hydrochloric acid. We have 0.00625 moles of hydrochloric acid. We have 1 mole of calcium chloride for every 2 moles of HCl, and that in turn gives us an expected yield of 0.003125 moles of calcium chloride. Likewise, if we try to calculate the moles of calcium chloride from calcium hydroxide, that in turn gives us 0.00625 moles of calcium hydroxide times 1 mole of calcium hydroxide per every, 1 mole of calcium chloride per every 1 mole of calcium hydroxide, which in turn gives us 0.00625 moles of calcium chloride. So which reactant is limiting? Which reactant is limiting? Hydrochloric acid or calcium hydroxide? Hydrochloric acid is exactly correct. So we're going to use the moles of hydrochloric acid when we write out our molar enthalpy. Okay. So continuing on with this idea, next we're going to calculate the heat of reaction. So we know that the mass of our solution is equal to the mass of the hydrochloric acid solution plus the mass of the calcium hydroxide solution, which gives us 50.0 grams plus 50.0 grams, which gives us 100.0 grams. Again, our density is 1 gram per mil, so we can convert our volumes directly to grams. Does anyone notice something a little bit interesting about this next heat exchange example? So before I let you loose to calculate the heat of reaction, I just want you to note, does everyone see this phrase about the calorimeter constant? Does everyone see that phrase? So what does that mean? What does that mean? Oh, it should just be joule per degree Celsius. Yeah, the calorimeter constant is just written as heat capacity, not specific heat. But the fact that we're given a calorimeter constant means that we have to account for the heat absorbed by the calorimeter in our heat exchange equation. So let's spend about 5 minutes and let's calculate the heat of reaction from the following data provided. And we'll discuss this example in about 5 minutes. Yep, and the response I see in the chat looks reasonable so far. All you have to do is fill in the numbers. And we'll discuss this example in about another 4 to 5 minutes. And if you have any questions or you want to submit your proposed response, we'll discuss this example in about another 3 to 4 minutes. And don't be shy to submit your proposed responses for the heat of reaction in the chat. And we'll discuss this example in about another 2 to 3 minutes. Don't be shy to submit your proposed response in the chat. Given the following information on the mass of our solution, the temperature change of our solution, and the specific heat of our reaction and our calorimeter, we have more than enough information to calculate the heat of reaction. Wow, and we even have a response that goes one step further and calculates the molar enthalpy. That looks quite good. We'll check the numbers, but the magnitude of that response looks perfect so far. Yep, the responses I'm seeing in the chat look quite reasonable, and we'll discuss this example in another 1 to 2 minutes. Just remember that our limiting reactant is our hydrochloric acid. But beyond that, the responses I see in the chat look reasonable, but you may want to re-enter your data in your calculator just to make sure that the calculations don't have any small entry errors. And we'll discuss in about another minute. Okay, so let's discuss this example. Thank you all for your input and your proposed responses. It's really helpful to get a sense of common questions that the class has. So we know that the mass of solution is the total mass of all of our solution components, both the hydrochloric acid and the calcium hydroxide. We know the specific heat of our solution is 4.18 joule per gram degree Celsius. We know that the final temperature is 23.30. And the initial temperature is 22.36. Okay, we also know the heat capacity of our calorimeter, it's going to be pretty small, is 72, whoops, one moment, is going to be 72 joule per degree Celsius. We now have all the information we need to calculate the heat of reaction, which is equal to -1 times Q solution plus Q calorimeter. So punching that in, Q reaction is equal to -1 times the mass of the solution, which is 100.0 grams, times the specific heat. One moment. Allow me one moment just to reset OneNote. Sorry about that. Sometimes it freezes up when there are a lot of things on the screen. Allow me 1 second just to reset OneNote and we'll complete discussing this solution. Okay, so we know the heat capacity of our calorimeter is 72 joule per degree Celsius. We know that the Q reaction is equal to -1 times Q cal plus Q solution. Okay, so then Q reaction is equal to -1 times the mass of the solution, which is 100.0 grams, times the specific heat, which is 4.184 joule per gram degree Celsius, times T final, which is 23.30, minus T initial, which is 22.36 degrees Celsius. Okay. Plus, now for the Q calorimeter, we have 72 joule per degree Celsius times T final minus T initial. So this is our Q cal, this is our Q solution. Now punching that into our calculator, that gives us a heat of reaction. Let me punch that into my calculator. That gives us a heat of reaction of -461 joules. Okay, and now what we're going to do is we're going to calculate the enthalpy of a reaction by taking the heat of reaction over the moles of our limiting reactant. And as long as we're very clear which reactant we're referring to, we'll have no problem with our enthalpy calculation. So that gives us 461 joules. and then we're going to divide by the moles of hydrochloric acid, which is 0.00625 moles of hydrochloric acid, which in turn gives us negative 73,756 joules. And we know that there are, in 1 kilojoule, there are 10 to the third joules, which in turn gives us negative 73.8 kilojoules. Let me write this up here. We have negative 73.8 kilojoules per mole of hydrochloric acid. It's really important that you specify your enthalpies in terms of kilojoules per mole. Kilojoules per mole. Okay? And moles, not just of anything, but moles of what? In this case, we're very specific. This is the heat generated, or this is the enthalpy of reaction in terms of kilojoules per every mole of hydrochloric acid that is reacted. Does this example make sense to everyone so far? Does this make sense to everyone so far? Any questions on this example? So this is a good stopping point for our lab lecture today. So let me just pause.